Okay, so date is 13/03 and we'll talk about GPT-1 today. The paper is, so you can just look for GPT-1 paper on Google and you will reach to the correct paper. The title is Improving Language Understanding by Generative Pre-training. Okay. So, what did we do in transformers? All these large language models, whichever you name, right, they are all transformer based models. Some are, so if you remember that photo that I had sent you in the beginning, right, the tree in the roots where you had word2vec, glove and fast text, and then so transformers was not mentioned there, but in all the three branches you had, one was encoder only, one was encoder decoder and third was decoder only. If you have a look at that, you will find that the other two branches are not flourishing as much as just the decoder one. So, what we had in transformers? What is the decoder only part of transformers? Right. So, you had things like so here we had, I mean, I'll just draw the decoder block once. So, decoder block was this masked multi-head attention and after that you had, what do we do after this? Add and norm. After that we do feed forward neural network and then again add and norm. This is our decoder only thing, because in decoder only what you don't have this cross attention here. So, no cross attention. No cross attention, obviously there will not be any cross attention because there is no encoder. Okay. Now, I will try to do this one zoomed up here. So, what do? You are going to take these x1s as input. So, this is let us say x1, x2 all the way until, what was the input size? What was t for this? 512. Okay. So, we have till this one. So, this is 512. Now, what do you do after taking this input? So, you have to compute, Q transpose K plus M. This is what you do, and this you are doing for everyone. See, whatever operations we are doing in this direction, we are doing it for every input. This is something we need to be clear in our mind. So, how many total parallel threads are going on here? 512. Whatever we are doing it for every xi. Okay. Next. So, what was this part? This is easy. So, you compute the q dot k, this is going to give you the attention scores, right. So, this is going to give you attention scores, that matrix basically. What will be the size of matrix in this case? It was 512 cross 512 in our last lectures, but right now each x1 is 768. So, of course, you are also adding the positional encodings here. So, these two guys are 768. So, what happens? This will be a, so you need to have 512 attention scores for 768. Okay, right. So that is what it becomes. Now what is next? Then we need to scale it. So this could have just, I mean, be done in the same thing. So you scale it with 1 by under root dk, and then you take softmax, and then what do you do next? Here you do dropout. Okay. What next? So what was the whole thing that we were doing in transformers? You take, so you compute the softmax of q transpose k plus m divided by under root k. This part is done. You take dropout. What is it that we were doing next? Which values? Right, multiply with values. Thank you. So what do we call that? Values. So shall I write values here simply? So let me just write some kind of values here. So multiply values. Now what do we do next? We have v of size what? This is, we are talking about just one head, right? So this is going to give me how many? This is going to give me a 64 dimensional vector, but there are total how many heads in GPT-1? There are 12 heads in GPT-1. So you will have, final thing will be 768. Okay. Now once you have this 768, what do you do next? So you have concatenated, you do dropout again. So 768 is what you have. After doing here, what do we do? Yes. Huh? For one head. See, what was the output for one head in our earlier cases too? 64, right? So I am not going to repeat that thing. This is coming exactly from transformers. Now instead of 8 heads, you have 12 heads. Okay? So, see, before taking softmax, so what you are saying here is, so I am not going to go into this why, let us see what might be happening here. So what might be happening here is, you have softmax, so you basically have probability distribution, right? So you, now how will this guy look like? Let us do it. So how will this guy look like? You before dropout, how will this matrix look like? So how many outputs here? This layer will be 5, 1, 2. No, I am just talking about one. Okay. So this one, and what is this last thing? Dimension of V is 64. So what we are saying here is, we will drop some of these connections, right? Give me some time to think. No? All right. So we multiply here. You concatenate that. What next they do is this concatenation is done. What was done next, guys? After this concatenation, you get 768 again, and right now this is just the output of my masked multi-head. And then you do add and norm. So what they say here is they do drop out. So am I missing some linear layer here? No, at two places they do drop out. So after coming out of this and before add and norm, also there is a dropout. Okay, and then you take the layer norm. So the only new thing that we have seen is you have used dropout somewhere in between. Okay, that's the only new thing. Rest everything is same as before. This is happening. So if you see, this path is just for one head. There are 12 such heads. Okay. Now, so this is your GPT architecture. हाँ, बताओ. Guys, what is head? Okay. See, your x1 is 768. So you need to compute these three vectors, query, key and value. So you need to compute, so before you go here, you need to compute QKV. Okay. Now, what will be the size of your, what were the size of matrices, guys? So what I want is a 64 cross 1. This is my query. This is what I want. I am multiplying it. So I am multiplying this 768 cross 1. So I need 64 cross 1. How should I multiply? So 64 cross 1. So what I want is 60, or we were doing it. No, wait. एक तो सारी चीजें मेरे से ही करवाते हो, है ना? So let's say this is my WQ, which I am going to multiply with XI, and I am going to get a query vector. Okay. So this XI is 768 cross 1. This guy has to be, let's say, 64 cross 768. That is going to give me 64 cross 1. Right? And you have, so if you have 12 heads, you have 12 such WQs. So one head gives you 64 dimensional Q. You will multiply same XI with WK, that is going to give me 64 dimensional K, and similarly with WV, that is going to give me 64 dimensional V. So now this whole thing is propagating until here, okay, until here. And you have this 64 here, and then 12 heads.
So, sir, इसके बाद 64, next 64 उसमें next parameters आएंगे, new parameters.
This 64, so तो ट्रांसफॉर्मर रिपीट करवा रहे हो यार तुम लोग, मतलब so this was coming from one head, okay, you will have another head. So another head will have its own QTW whatever, scale, softmax, dropout, multiply with V's from that particular parameter matrix and multiply with the V's from that particular heads parameter matrix of, right, coming from V. That 64 will come here, 12 such things, because in the end you may want to make it 768 dimensional. Okay? Questions? Done? Okay, okay. So this is done. See, I think the best reason that I will do away by saying about dropout here is, there are a couple of changes we will see in GPT-2 and GPT-3 as well, right? But only small changes to this complete architecture. The whole thing remains the same. So right now I'll simply say this is probably the best place to do this, because once you have taken a softmax, you have these probability distribution. What you are essentially trying to say here is, in computing V, don't exclusively depend on all of them. You can randomly drop a few, but whatever next question that you are going to ask me, right now I am not capable to answer that. Okay? So for example, if this is the node I was depending the most on, and if this guy gets dropped, whom should I pay attention to? Hmm? Sorry? No, so the point here is, this won't happen often. So let's say if you are dropping 10% of the neurons, you are not dropping too much, right? So with very high probability, you will be dropping only those neurons which are insignificant to you. Once in a while you will drop neurons which are important to you, but that's okay.
तो सर अगर हम यहाँ पे ड्रॉप आउट कर रहे हैं, फिर वापस हम मल्टीप्लायर वी के बाद में फिर से ड्रॉप आउट क्यों कर रहे हैं? मतलब दो बार क्यों कर रहे हैं? फिर एक ही बार कर लेते हैं.
No, see, regularization is something, try to do as often as you can. See, what is the downsides of, see, this is a big model, and what are the downsides of a big model in any machine learning thing? So if you have high capacity model, that tends to overfit, because that has too many parameters, right? Remember that basic thing, if you have this data set, right, maybe you would like to fit a line, Prapti. So if you have this data set, maybe you would like to fit a line and probably not this function, okay? And probably not this function, because why would you like to fit a line and not this function? Even though this function gives you 0 training error. Exactly. I repeat this thing, even if you were to do 50 courses on machine learning, what will be the goal of each of those courses? Generalization. So your algorithm should generalize well. This first one gives me 0 training error but does not generalize at all. Whereas this line, it gives me quite a high training error but generalizes much better. So for example, if a new point comes here, this is going to give me this loss, whereas line gives me just this one. Okay. So simpler models, they generalize well. Dropout is the best known regularization technique in neural networks right now. Okay. So basically idea is to do dropout as many times as you can. Remember when we were doing deep neural networks, we said use dropout everywhere. So I think, so why can't you use it before? That's a question that I don't want to get into right now. But idea is use dropout as often as you can. So rather than asking this question, why dropout here and then why did we do again here? The question should be why didn't we do at every layer? Okay. So I mean they might have tried it, but let's say putting only here and here gave them the best results. Right. So ideally regularize everything. Layer norm, what next? So then things are repeated and nothing changes. Okay. Of course, when you see feed forward network, you will drop out there too. I mean, feed forward networks are, we have seen. No, this one. Sorry. हाँ. You do drop out layer wise.
सर बट न्यूरल नेटवर्क में से सिर्फ हिडन लेयर की तो ड्रॉप आउट
Exactly. हाँ. I mean, what is the question?
क्वेश्चन यही था कि किस जगह पे लग रहा था उसके अंदर तो अपन सॉफ्ट मैक्स के बाद भी वो लगा देते हैं.
See, so you have, how does पूरा ट्रांसफार्मर रिपीट करा लो तुम लोग. So this is 768, this is 3072 for GPT 1 and this is 768 again. Okay. Now you drop out here. Okay. Sure. This is my whole thing. So once you have, this was the layer norm here, then you do feed forward neural network, then you do add and norm, and then you get the final output. So what will be the final output size? 768, right? So this 768 vector, this is basically my, what is 768? What is the name for it? D model. What is D model used for? The embedding size that you assign to your input vectors and positional encodings, and that is something you keep throughout the network. Okay. Now, how many such layers are there? How many layers are there in GPT-1? How many layers means how many decoders stacked over each other? 12. So basically number of layers of decoders. What else? Yes, what else? Number of attention heads. So number of attention heads is 12. The model we have already seen is 768. What else? T is our 7512. This is something that I have been taking throughout, starting from transformers lecture. Anything left? Parameters. Which parameters?
Number of parameters.
वो मैं पूछूंगा तुमसे. Okay. I don't see anything, and So I think given these, you should be able to compute everything. So you start from X, you compute QKV, then you compute softmax, then you concatenate. Okay, so but we have done it before. So just to reiterate, how does each feed forward network look like? 3072. Of course, it has to receive a 768 dimensional thing and output a 768 dimensional thing here. Okay. I think with this, the description of, so let me just read the paper. So we trained a 12-layer decoder only transformer, 768 dimensional states, 12 attention heads, 3072 linear inner states. They use Adam optimizer. So train for 100 epochs on mini batches of 64 randomly sampled contiguous. Okay, so we can start talking about training now. So they say they train for 100 epochs. Batch size is 64. T was 512. Right? What else you will have? So 64 batches of size 512. What does this mean? From your corpus, you randomly choose 64 contiguous blocks of 512 words right now. Remember, I am saying words and not tokens. Or even if I say tokens, for me right now, tokens is same as words. Okay. And they use spacey tokenizer. Okay. So, okay, now I see. We use a byte pair encoding vocabulary with 40,000. So mod V is, they say 40,000, but I think this is actually 4478. Okay. And residual embedding. So now you see dropouts are here. At residual connections, they have dropouts, embedding and attention dropouts with a rate of 0.1 for regularization. So how many neurons will you drop randomly? 10%. Okay. And then say we also employed a modified version of L2 regularization. And they, so which activation function is used here? GALU. I am not going to cover this, you can go and have a look at this. This is just a continuous version of, I mean a differentiable version of ReLU. Okay, and their training data set. The training data set is some books corpus. I think if I remember it right, they had some 7,000 books that had roughly I think 74 million sentences, but not sure, and somewhere around 1 billion words. somewhere around 1 billion tokens if I remember it right, but I am not sure. So that is it. This is about the architecture of GPT-1, and this more or less stays the same for all the way until GPT-3 with minor changes. GPT 3.5 we don't even know what they exactly did. Until GPT-2 paper they are revealing everything. GPT-3 they withhold somewhat, but 3.5 is something that is completely a black box. Okay. But we will try to see that anyway. I have not gone to that part right now. I am about to go there now. So what do they do with this architecture? What do you want to do with this? I mean, you are training so much. What do you want to achieve? So right now see, so they state a few things that I am going to read here. See, this paper was published in June 2018, and just before that, around in October 2017, Transformers paper was published, right? So once Transformers came, they actually transformed everything, at least in NLP, not so much in vision, but at least in NLP, they were quite transformative. Now, until then, what was NLP community doing? If you want to do NER, what are you supposed to do? You should have a lot of examples, and for every word you are supposed to have a label that this is a named entity 0 or 1, or you will have some other things like question answering, or you will have, what were the other NLP tasks? Sentiment classification, right? So you had all these different tasks. You were annotating different text corpus suited for that task. So how will you do NER? You have this, x1, x2, you have, this is your corpus, and for every word you have 0, 1. Zero, 1. How were you doing sentiment classification? How were you doing sentiment classification? So you will have one example. Now example 1 is nothing but a combination of different words, okay, and you will assign sentiment. So it can be, let's say, positive, negative. Let's say I am keeping just 3 classes, neutral. So you will need to make a data set where examples are there, and you need to annotate each example as positive, negative, neutral, then train on that particular data set for this particular task. The paper claims, as a human being, you were never taught to do this kind of sentiment classification at any level of your education. You just know language. But if this task is given to you, then it is no brainer for us to be able to figure out whether a particular sentiment is positive, negative, or neutral. We don't need to be trained on this particular task alone, do we? So their claim is, their idea is, let's make a model which will have a very good understanding of the language itself, right? And then I will ask them different questions like sentiment classification, NER, question answering, and so on. And then we will see whether my model has actually done better. What they show here is they train this transformer GPT-1 and then they use that pre-training, fine tune it on these tasks, and they say that out of 12 tasks, on 9 what happened? They outperformed the state of the art individual networks for all these problems. So let's say you were doing a LSTM that was designed specifically for solving sentiment classification. This GPT-1 pre-trained and fine-tuned on sentiment classification actually worked better than the previous best, whatever it was, and it was LSTMs then. Okay. So what is the one-line summary of this whole thing? You don't need to make neural networks separate for each problem. You learn this one big thing called GPT-1 in this case, and we assume it will have enough information about language, and then use that encodings to do any of these tasks. It turns out it does pretty well. Take ChatGPT, GPT-4 now, right? You can ask it, it will do NER for you, it will do translation for you, it will do all sorts of language specific tasks. So we were talking about training now. Pre-training. So what is pre-training? Whatever we just saw above, you are pre-training that architecture. Okay? And what does pre-training mean? Right. So you have this data set, this book corpus of roughly 1 billion tokens. You train on that. What is it that you are going to train? So how will you do the training now? Let us just do this part. So I am just calling it transformer now. In fact, I am calling it GPT-1. And you know what is there inside this? There are 12 layers, each layer is feed forward and so on. Okay? So you give inputs here, x1 to x, 512. What comes out here? What are you supposed? So this is my y1 hat. What should be y1 hat? So what are you doing in the end? At all of this, what are you doing in the end? Right? Even though I have drawn it outside GPT-1, but it is actually inside. So what are you doing? Softmax, and this will be softmax over how many? You always do softmax over your vocabulary size, because which word you are going to choose next, that is what you are supposed to figure out. So this softmax will be a probability distribution over your vocabulary size, which is what in this case? 40k. Okay? So you assign probability to one of them. Now what are we going to do? Do we feed whatever is the output, do we feed it here? Yes. So whatever do we output, do we feed it here? No. Right? What do we do instead? so as I have read that, so this is from my training data. Okay. Now, so you don't feed, so this guy is not coming here right now. What was the reason for this? What was the reason for this? You should know this. But in the end, your goal is to be able to predict the next word. No, see, initially when you are starting to train, these parameters are random. So they are going to give you some random output here. A random, so garbage in here will give you garbage out here again, right? So this won't make sense. So initially, not towards the end, initially what you do is, this guy is just x2 and this is not y1 hat. So this is not y1 hat, okay? And this method is called what? Even though your network has predicted something, you don't use that for the next output, because you know this guy was garbage and this will only propagate garbage. Okay? So this will only delay my learning, nothing else. Eventually network will be able to figure out, but that will only delay my learning. Now question here is, what is y1? So what are you supposed to do in the end here? You are supposed to give me the this is probability of x1. What are you supposed to output me here? Probability of x2 given x1. What will be final thing here? Probability of x512 given x1 all the way until 511. Okay? How do you compute this? I mean, what loss can we use? Very standard thing. What was cross entropy? So cross entropy was, I'll first write these things. Where should I put heads? Where should I put heads? So inside log, right? What else am I supposed to do? This whole thing, summation over all my examples, take average and take minus, because you are supposed to do gradient descent. Okay? Now, here we had two classes. There was class y, which can take either value 0 or 1. So if class is 0, other class can be 1. If one class is 1, other class will be 0. So this is your class 1, this is your class 2. And you will have outputs corresponding to only those things. Here in this case, how many classes do you have? Here in this case, how many classes do you have? Mod V. So, you have mod V classes. How will this thing look like? And here I had just examples. So, how will this thing look like now? Remember, we did something like this. Right. So this is how your one hot vector for a particular xi looks like. So for a particular xi, this is mod v cross 1, one hot vector, somewhere you will have 1. And what about your output? That is also mod v cross 1. Right? And here you will have y1 hat, I mean not y1 hat, sorry. Here you will have probability of 1, probability of 2, all the way until probability of mod v. Right? Mod v minus 1 terms are 0 here. All these terms are potentially non-zero here. Now, how do you multiply things? So, take log of this . Dot product you can take if you want to. So, only this guy will multiply with the corresponding pi here. So, if this is my ith place, if this is my ith place, I will get multiplied with just pi. So, basically I am rewriting that same equation above. What I will be writing here is something like log pi, because all these terms will be 0. So, what will happen to this? Let us say if you have class 0, what will happen to which term? What will happen to this term if y is 0? Goes away. What will happen to this term is if class is 1? Goes away. Okay. So, similarly here you have mod v classes, but all mod v minus 1 will go to 0. Only one guy will be non-zero, for which the class we are talking about. Now, you are doing it for how many words? So, I am trying to compute the total thing now. So, t equal to 1 to 512, okay, and this is for just one batch. You are supposed to do this for all batches. So, I am not going to write this whole summation, right. This gives you your loss j, whatever you call it. This is what you are pre-training on. So, all batches and then as many training iterations as you have, so you can have a third summation here. Or can I simply replace this whole thing by corpus? See, one iteration will have 64 batches and as many iterations as you have. So, right thing will be to do one more summation over iterations. This gives you the complete loss, okay. And but I am sure there is some better way of representing this. Um, I don't see that here now. Okay. Or in fact, I could have just kept it summation log pi. That was a better way, right? Summation log pi for all I that I am trying to predict. Okay. So that is your training objective here. You train this whole network on this task, that is, how do you predict the next word? Last 2 minutes. So what was this fine tuning? Or let's say we'll do fine tuning in the next class. Questions until now? Any questions? You won't come here and then ask?
सर ये मतलब इससे तो अभी अपन केवल यही प्रिडिक्ट कर रहे हैं ना अगला वर्ड क्या है.
Exactly. So their big claim is this. Their big claim is this. I want my network to learn what is my next word in this sequence of tokens. And their claim is, if your network learns just this thing, it learns a lot about language, all these subsidiary tasks, NER, sentiment classification, question answering, they become super easy once you use this kind of a learned network. More questions?
तो सर वो मतलब चैट जी काम कैसे करते हैं क्वेश्चन पूछते हैं वो चीज़ है.
No, right now we are talking about GPT-1, not Chat GPT.
तो सर वो कब पढ़ेगा मतलब GPT-3 के अंदर आएगा.
GPT-3 will cover a bit of it, right? But I will try to do that thing after we are done with the hands-on thing. So I'll first cover GPT-1, then BERT, then GPT-2, then T5, then hands-on, and then if time permits, we go to ChatGPT. But broadly, even ChatGPT is the same. You do some kind of reinforcement learning, so RLHF, right? Reinforcement learning from human feedback. That is a new thing that you do. And there is yet another paper by OpenAI called Instruct GPT. I don't think time will permit me to do that. If we cover all these things, ChatGPT whole thing is answered. But even that is closed source. Chalo, done for today.